Okay, good morning, everyone. Welcome to the second and last morning of this meeting. We have now 4 talks, the coffee break, and then the discussion. And the first speaker of the morning, you have him here, is Haibo Yuan, talking about the JAST80 L2.0 project. You can start, you have 20 minutes, okay?
Okay. So can you see my screen? Okay. Hello, everyone. My name is Haibo Yuan from Beijing Normal University. So today I'm going to tell you a story about ongoing space mission. It's named Earth 2.0 ET project, aiming at detecting Earth-like planets in a habitable zone. And in this story, I believe J+ can play a very important role. So the story starts from a very long-lasting question in the history of humankind. Are we alone in the universe? Fortunately, the astronomers can now try to answer this question in a scientific way. And the Nobel Prize has been given to astronomers who reported the first discovery of solar planets orbiting a solar-type stars. And also in the very recent US decadal survey, the pathways to habitable worlds is listed as the top priority area. So detecting habitable Earth-like planets is one of the key questions for the astronomy. It's a long story, but to make it short, we start from the Kepler mission. The Kepler is a very successful mission that it monitored 200,000 stars for 2 years, and it has detected thousands of planets. And therefore, it has revolutionized the field of extrasolar planets. However, from the bottom left panel, we can see that the Kepler planets are mostly super-Earth or sub-Neptune, and there are very few Earth-like planets, and there is no Earth-like planets in the around solar-type stars. This is because of many first reasons. One is that it's a small field of view, so and also the very limited number of stars that can be monitored. And the second reason is that it's large without noise. It's over 100 electrons per pixel, and also it's non-optimal temperature control can lead extra photometric noise. The last one is stellar noise is larger than expected. Therefore, in order to find Earth-like planets, we need targeting more stars and quiet stars with better precision. And this plot shows the stellar noise from the stellar activity for the Kepler stars of solar types. So we can see that it's most stars, they have variability larger than our solar. So that's this stellar noise can hidden the signal of the Earth in the light curves. Therefore, Professor Ge Jian from Shanghai Observatory proposed this Earth 2.0 mission. Now this is this satellite. It has 7 telescopes of 30 centimeter in aperture. So 6 of them will pointing to the Kepler fields and do the transit observations. And the field of view is 5 times larger than the Kepler. It's 500 square degree. And there's another one pointing to the galactic center for microlensing detection of extrasolar planets. For the transit observations, we will use the low readout noise CMOS detectors and staring at the fields, the Kepler field, for at least 4 years and monitoring over 1 million stars. So the number is also 6 times of Kepler. And the satellite is scheduled to be launched in 2026 to the L2 orbit. And now we have a very broad science team from over 30 universities and institutions from China, US, and Europe. So now it's some science cases for the mission. The first is the extrasolar planets. So the left panel shows the simulated ET discoveries in the orbital period and the radius diagram. And the black dots are the Kepler discoveries. So we can see that ET will identify about 40 Earth-like planets in the habitable zone during 8 years operation. So it will become a true breakthrough for the current non-detection. Also, it can identify over 40,000 new planets. So it's like 20 times more than the Kepler, and including over 8,000 Earth-like planets around solar type stars. This will provide a very diverse sample for the detailed studies of the planet distributions, their properties, architecture, and formation, and also to study how planets are related to their host and the environments. And their host stars can be also be precisely characterized with the stellar seismology technique. Now for stars, we know that Kepler has not only revolutionized the field of extrasolar planets, but also the stellar seismology. And for ET, it's long. The timeline is longer. The star numbers are larger, and therefore it will provide a much larger and better database for stellar seismology to address the key questions like the seismology of the main sequence and subgiant stars, and also using this long-term baseline observations to study the stellar rotation, to understand the angular momentum transport problem, and also can perform seismology studies of luminous red giants. And for the galactic archaeology, we know that stellar age is the key parameter for galactic archaeology, and the stellar age can be mostly precisely determined from seismology. Kepler has delivered precise ages for a few thousand stars, but all those stars are mostly metal-rich stars. There are only very few metal-poor stars. And with ET, it will deliver precise ages. It means 5 to 10% for over 6,000 metal-poor stars. So it can reveal the formation and evolution history of the Milky Way at its earliest epochs. Also, ET will deliver the benchmark sample for stellar ages and parameters for large spectroscopic surveys, we know that the Kepler field is a very hot field that almost all the spectroscopic surveys in the Northern Hemisphere will observe the Kepler fields. So why J plus is involved and why it's important? This is because that even ET can monitor more stars than Kepler, but it cannot monitor all the stars in the field. Therefore, target selection is very important. For example, we need a complete catalog of high precision stellar parameters, including the temperature, log G, metallicity, and alpha abundance in the field to select the mean poor stars. And we need those parameters to select targets for seismology and also for the follow-up analysis of the. In addition, we also need time domain observations to select the quiet stars to enhance the rate of detecting Earth-like planets. And as we know that the J plus is a machine for stellar parameters, so it's the most suitable telescope for such kind of work. With these optimized filters, very precise stellar parameters can be determined from the J plus filters. For example, using the machine learning technique, we can determine its temperature to a precision of 50 Kelvin, log G 0.1 dex, and metallicity 0.07 dex. So it's comparable, even better than the spectroscopic surveys. And not only those basic stellar parameters, we can also determine the individual element abundances, such as the carbon, the magnesium, nitrogen, and the calcium. And for those individual element abundances, the precision also is about 0.04 to 0.08 dex. And those determinations are very reliable. So here I show you the example how we can determine the magnesium abundance from the one of the J plus filters, the J0515. So this filter it captures the magnesium triplet. So this panel is the color diagram. So the x-axis is the Gaia BP minus RP. The y-axis is the BP minus the J plus filter. So for each column, it represents stars of very similar metallicity. And the colors represent the magnesium abundance. So we can see that in this color diagram, the stars of different magnesium abundance, they are well separated in this color diagram. So it means that we can determine magnesium abundance from this color plot. And for the time domain survey, we propose a new narrowband filter centered at the calcium K line to monitor stellar activities. As I mentioned before, the stellar activity is the main noise in detecting Earth-like planets. The red panel shows the Kepler photometric precision as a function of S-index. So S-index is an indicator of the stellar activity. So we can see that for quiet stars, the precision can be much better than the active stars. So that's why we need a time domain survey to monitor the K line, which is a good indicator of the stellar activity. Okay, here the survey strategy. So we are going to use the 12 J plus filters and a new very narrowband filter centered at the K line. And we need 300 fields to cover the whole ET footprint, which is 500 square degree. And we need 3 exposures, the short one, the medium one, and the long one, to cover a very wide magnitude range for stars brighter than 16 with high precision photometry. So it will take about 500 hours. And for the time domain survey of cell activities, we need monitor each star for like 10 to 15 times. And it will take 700 hours. And if the ET satellite can be launched on time, so which is 2026, then we should complete the survey before the launch of the satellite. So okay, here's the summary. So with the T80 telescope, the J+ filters, and the new narrowband filter, we propose a photometric and time domain survey of about 1.7 million stars brighter than 16 in the capture field for the target selection and the characterization of the ET satellite. And the strong synergy between the J+, ET, and Kepler will provide invaluable legacy data for addressing the most fundamental questions of planets, stars, and the Milky Way. So here is the current team members, and you are all welcome to join. So thank you.
Okay, thank you. It was quite fast. So we have plenty of time for questions. Is there any question here? Yeah, wait.
Yeah, my question is in relation with the ET mission. Just wanted to know how it compares with, for instance, with Plato. It's a mission that is going to be launched in 2026 and is expected to observe of the order of 10,000 Earth-like planets.
Okay. So Javier is asking how this ET mission compares to Plato that will also be launched around 2026.
I'm not familiar to Plato, but as far as I know, Plato will observe, I think, the bright stars and sorry, I need to I'm not familiar to the Plato, so I need to look up something. So I can't answer this question right now. But I think there is a very I think it's very different when the ET team proposed this concept. They compare it with Plato and even the Roman space telescope. So they think they are very competitive to those telescopes. But I don't have the very detailed numbers.
Okay, no problem. Any other question? In the chat or... Andres, what? Okay.
So, yeah, this is a question from the ignorance. Is the Kepler field already within the footprint of the A+? And if so, apart from the time domain and observations, what will be the difference between Kepler and J+?
Yeah, so Andres is asking about the the field that you plan to observe, if this is already observed with J+, and if that's the case, if there's more about the time, in addition to the time domain science.
Can you repeat the question?
Yeah, sorry. Andres asked if the field you plan to observe is different from the J+.
Yes, the current J+ filter here is centered on HK line is like 100.
We are not hearing you.
Hi, Haibo, are you there? We can see your screen, but we cannot hear you. I see him in the. I see him online.
Yeah, yes. It might be us, but we are not hearing. No.
I don't think so. That's why. Oh. Desmuteate y habla para ver si sale por ahí. Para ver si somos nosotros.
Hola, probando. Sí.
Bueno, repasemos aquí.
Yeah, then it's time.
Can I just go to share the screen?
Do you want to share the screen?
Yeah, perfect.
Sure.
So we are going now to the next speaker, Tomaz Zwitter. He will talk about stellar chemistry from photometric narrowband imaging. Let's go. You have 20 minutes, okay?
Thank you very much. I hope you hear me and you see the screen.
We see your screen.
Okay, good. Okay, so this will be a talk you should be familiar with. So we are speaking about narrowband imaging. And it will be focused mostly on Plato, as you will see. And while this comes, of course, from the letter of intent, which was led by Luca Casagrande, who is also now online. Of course, you know Luca, very active in various spectroscopic surveys like GALA and also photometric ones like StarMapper. And well, I don't need to introduce Luca anymore. Then we have Aldo. Aldo is, of course, from Bellaterra, close to Barcelona. And well, he's an expert in asteroseismology. And of course, this is very much relevant to Plato again. And then we have Andrea Chiavasa from Nice, who is, of course, an expert on stellar energy distributions, computation of three-dimensional stellar models like the staggered grid and so on. So, of course, he supplies us with necessary theoretical input. And there are a number of other people, of course, involved. For example, the Raul Michel Murillo, who actually provided this kind of beautiful test images of various galaxies taken in the three filters. And now you see which filters I'm speaking about. So there are the right one would be centered on the calcium H and K lines, of course. Then the 430 is centered on some strong iron lines, and 450 is a kind of continuum filter. I will, of course, speak about this later on. So let's see. Okay. So First thing, of course, is why we do that. And the reason is we want to use photometry to determine stellar parameters. And as you know, magnitude of a star is related to its parameters, like stellar flux, which depends, of course, on temperature, log G, various chemical abundances, and so on, and of course, your filter throughput. Now you can use this kind of magnitudes, as we all know, to determine these stellar properties. And of course, it depends on which filter you choose, what you're going to see. And of course, this is old stuff. I mean, this is plain from the textbook. This is done essentially for decades, so to put it, okay? But I mean, there are various approaches to that. And one approach is to use broadband filters. So this is classical approach. We all know Sloan, Gaia BPRP, PAN-STARRS, Tomaz, and so on. Here, we are sensitive mostly to effective temperature. Then we have intermediate band. Intermediate band photometry, while it was pioneered on a large scale by the well-known Geneva-Copenhagen survey, and recently by the SkyMapper in the south, I mean in Australia. And while the advantage here is that you can actually get also the metallicity and surface gravity, and maybe to some degree indication about the chemistry of the star. And then we have the narrow band. Narrow band, for obvious reasons, was not very popular in the past. We, of course, know about the Pristine survey. But if we are speaking about large surveys, I should really emphasize that J+ done on the JAST80 is really a terrific example of what you can do with narrowband photometry. Now, the situation actually is changing now, and that's the important thing and the reason for our proposal, because now the photometric surveys can use information from Gaia, and you can use the distances. And this essentially from colors, you have very good constraints on temperatures, and from luminosity also on surface gravities. So suddenly all this degenerate field of using photometry for everything, while you don't need to do this anymore, now you can really concentrate on chemistry, because other things are possible to be done by Gaia to a large degree. Now, you would say, well, do your chemistry from spectroscopy? Yes, of course. I mean, this is the way to do it. But there are a few edges where photometry has an advantage. I mean, so if we speak about that, about spectroscopic surveys, well, of course, you get chemistry, radial velocities, not affected by reddening, a lot of advantages. But normally, even if you do many stars at once, your fiber machine allows you to put maybe 100 stars per square degree, and these stars should be relatively bright. Typically, if we are speaking about 4 or even 8 meter telescopes, we are speaking about magnitude 14 or this kind of. Then the important thing is you need to pre-select your targets, where to put your fibers, because if you don't put the fiber on a certain star, of course, it is not observed, and even though it is in your field, you are not going to get it, okay? And then there is also a small problem with the magnitude range, because, of course, for obvious reasons, in my experience with RAVE and also with Gala, we are limited to something like 2.5 magnitudes at most, I mean, in difference in magnitude, because otherwise simply the star gets too bright or too faint to get useful information. Now, to put this into the context, of course, we can do few million stars. For example, all spectroscopic surveys combined now have of the order of 8 million stars. From this, a good fraction would be Lamont. Gala is now approaching 1 million, you know about other numbers, not important at the moment. But anyway, a vast majority of Gaia stars has no spectroscopy. And therefore, what we can do with photometry, well, of course, you are limited by pixel scales, but this is still at least an order of magnitude denser than what you can achieve by fibers on a large field. Then there is no pre-selection of targets. Whatever is in your field potentially could get reduced, and you get the information on. And then you have a very simple trick of using short and long exposure, and therefore expanding vastly your magnitude range. And this is, of course, important to get both the bright targets, maybe for planet searches, and the faint ones for which you really have no idea about chemistry. Now, what to choose about chemistry? We should be a bit modest here, not like spectroscopy or Galau, which determines up to 30 elements. We want essentially to have two numbers. One is iron abundance, or let us call it metallicity, and the other one is abundance of alpha elements. And the reason is that these are perfect diagnostics for stellar population studies and do also other tricks, as we all know, and I will explain later. So we have this kind of, let's say, textbook diagram now from Matteucci review. And as you know, alpha abundance, alpha elements come mostly from type 2 supernovae, while iron comes mostly from type 1a supernova. At least it is produced only, only iron is produced by this supernova. Then we are having, in this alpha versus iron plot, we are having a plateau and a knee, and this is related to the initial mass function and to the star formation rate. Then, as we all know, alpha elements are a good proxy for the stellar ages, the thing which is difficult to determine otherwise. All this then allows us to chemically dissect the different galactic components. So yes, we do need these two axes. And these are, of course, chemistry. So what can be done by photometry? Well, you need to choose your filters, which are now sensitive to these alpha abundances and iron abundances. What we did here is we used a range of stellar templates for the main sequence stars on the left and for the red giant branch stars on the right. And now the size of the symbol is parallel to the sensitivity of iron if it is a red symbol, and alpha if it is a blue symbol. So what we want is a cross-section of, let's say, two pairs of wavelengths, altogether three filters, where you would have a large blue and red dot on the same line. And also we would like to have the dot close to the diagonal line because we want to have all three filter wavelengths nearby and therefore be less sensitive to the observing conditions, atmospheric extinction, also possible errors in temperature determination and so on. And as you see, for good reasons, we actually landed on these three filters. A is a continuum filter at 450. B, as said, is iron line complex at 430. And C is, of course, the calcium H and K lines. I would like to mention that these filters are actually covered also by the present setup at the telescope. That means B and C are straight J430 and J395 filters. About the A, well, A is now Galante F450N filter, but if needed, perhaps also judging from this diagram, you could replace A with J410 because this is another continuum region. I mean, if needed, if this is for operational reasons more convenient, okay? Now, of course, we went a bit deeper than the previous diagram, and this is now the behavior versus temperature for main sequence and for red giant stars. And the full line tells you how a certain color index, CA-A or B-A, is changing if you are replacing a solar type star with a metal poor non-enhanced stars, while the dashed line is the same thing, but for alpha enhanced. And as you see, the full and dashed lines do not follow each other. They're simply shifted in giant stars and a more complicated behavior versus temperature in main sequence stars. But this gives you a hope that actually you will be able to recover both of these axes. It's not a trivial one-to-one relation, but I mean, these two color indexes, at least in principle, allow you to do that. Now, as I said, I mean, these filters are very close to what is already available at the telescope, while we are not observing at JAST80. So we use simple Edmund optics filters. Here we have in blue the part numbers of these filters. This is important because, when you do a survey, you would not like that the JAST80 will be alone and never to be replicated anywhere. And of course, people around the world can use this Edmund optics, which is readily available, and actually use it at its own telescope, which is important. Of course, these filters are smaller, just 50 millimeters, so not suitable for the JAST80 telescope, but I mean, still very similar properties, right? Now, all this is theory, and of course, we want to have some proof in reality. This is the goal of the ongoing ESA projects, which is called Photo to Chem, so photometry to chemistry. And it is intended as a kind of proof of concept for Gaia, Plato, and also to some degree for the Gaia near-infrared missions. We are using some pilot observations at the moment, 2 telescopes in Slovenia, one at Črni, which is quite known for the discovery and follow of the comets and asteroids, and the other one at our university, a 70-centimeter telescope. So these are much smaller field of view, of course, but well, also smaller in the collecting area, of course, than JAST80. And then in this kind of project, you don't have standard stars. I mean, you don't know what exactly will be the magnitude of a number of stars. I mean, but you do have parameters, and we have parameters from spectroscopy from both apogee in the north and Galau, which is around the equator, and then further down to the south. And we use these ones as benchmarks. And these are now the very preliminary results of how you could hope to determine the iron and calcium abundances if you use the benchmarks from apogee. Of course, apogee because our telescopes are quite far in the north. What you have plotted is the medians in various iron abundance and calcium intervals. I should mention, of course, that on the points which are at the bottom of each panel corresponds to low iron abundances and low calcium abundances, and these kind of stars are rare in our sample of a few thousand stars observed so far, therefore quite uncertain. Well, these are medians, so the scatter would be at the moment of the order of vertical distance, or a bit smaller than the vertical distance between the various median points. We are improving on that. As you see at the moment, for the horizontal axis, we are simply using a combination of the observed filters, and the log G, of course, comes from luminosity in Gaia, which is easy to determine for giant stars, which are demonstrated here. So this kind of relations tell you, yes, it is possible, and it is working in the progress. Another 6 months to go, and we hope to have these relations even cleaner. Then, well, if you have now the setup, you need to choose your field. And yes, we are mostly concentrated on the Plato North long duration field, but we note that the TESS continuing viewing zone, another, of course, planet hunter, is very much nearby, and also this partly overlaps with the Kepler field. So the idea of the proposal, which we are going to submit, I believe, is that we would like to have chemistry for the solar-like oscillations in some 100,000 stars. Then, of course, it's also Plato is a planet hunting mission. So for the bright stars, we want to have, again, this kind of information. And then the important thing is that if you have stellar metallicities and alpha, then you really know what to do about astroseismic ages and the distances. And of course, as I said, this helps you with the exoplanet statistics and the general legacy value of the Plato observations at all. I mean, then in this field, there are not only fit stars, but we have also 6 open clusters, 4 globular clusters. So then hope to have some sensitivity to the rotation rates of turn off stars in open clusters, and of course to judge the multiple populations in globulars. Well, about the observing strategy, Well, the important thing is we can use iron and alpha to have all astroseismic detections in the long duration Plato field. Then if you compare ABC filters, so this which I mentioned, to the Gaia BP spectrophotometry, I would like to note that if you look closely, the Gaia BP has a dip in sensitivity around calcium. And therefore, it is not very suitable to use calcium for alpha abundance. And of course, this survey is filling this gap. So Gaia is not competing in calcium to the ABC on the JAST80. It can use, of course, the magnesium triplet at 515 and further to the red. And as we saw in another graph earlier, yes, that's the reason why perhaps it can do something for giants. But I mean, calcium is perhaps difficult. I mean, then we need to, in observing strategy, think about reference stars. And at the moment, we think about spectroscopic surveys, which actually much scarcer, but they cover these fields. We are speaking about apogee, of course, about Lamoste, and for bright stars also about Gaia itself. The goal is, of course, to obtain at least signal to noise 100. And in the letter of intent, we made a quick calculation, and this requires of the order of 30-minute combined exposures in ABC filters. And then the Plato field has some 2,250 square degrees. So this translates into 600 hours or 1,200 pointings. Then you would like to have a modest overlap of these pointings because of control of the variability of the targets, at least in statistical sense. And of course, there is also the weather creeping in. So of the order of 800 and 900 hours is what is required for the coverage of the complete Plato field. And so to summarize, while the important thing to stress is we are in a new situation with Gaia DR3 and of course already with Gaia DR2, we now have a good handle on temperature and luminosity, but not on chemistry. And here comes the huge potential for this kind of narrowband imaging, because in Gaia you have 160 million stars which are brighter than G = 17. And for most of them, iron and alpha abundances will not be achievable by Gaia. Then, as I said, Plato will get chemistry for all astroseismic targets, and this is, of course, of tremendous value for the success of the mission and for astroseismology in general. And then, while Plato will be also a big legacy value, and of course, having the narrowband photometry helps here substantially. But then there will be a successor to Gaia. We just submitted a white paper. It's now published. And while the important message is Gaia near-infrared is not thought to have any spectroscopy on board, while of spectroscopy, of course, get multiplexed by fibers, but still it is a very modest compared to the number of targets we are having. So chemistry, I believe, on large scale can be done only via narrowband imaging, and this kind of JAST80 project can actually serve as a kind of teaser or motivator actually to do this another survey also for the Gaia near-infrared. As I said, the good thing is some of the existing filters are actually matching what we want here, so no need for new equipment. And then about the pilot survey, I just showed you a few of very preliminary results. As I said, it's another 6 months to go. And so roughly at the time we plan to submit the proposal for JAST80, we will have better results, I believe. And of course, JAST80 is another game because while we extremely appreciate, really very much appreciate the huge field of view, this is essential. And also, you know, the observing conditions you showed yesterday, this is impressive. So I think that this can be good use for JAST80. And well, I will stop at this point. Thank you.
Yeah, thank you, Tomaz. So there's some questions here, the audience. Yeah, Alessandro.
why are you using apogee as a benchmark stars rather than, for example, Segre or Lamoste?
Well, the reason is, well, I was a project scientist of RAVE. Then we drifted, of course, to Galat. Galat is excellent, but at least if you do your pilot observations from Slovenia, you are 46 degrees north, and therefore only some fields around the equator are okay. Then, well, the straight answer to your question is there are two items. One, we demonstrated that Apogee and Galat are really compatible. This is important because you want to have your set of, let's say, even future benchmark stars across the whole sky, right? And the important thing is, well, as you know, Apogee is now having also a part which is Apogee South. But anyway, the important thing is the reference system is really compatible. Lamoste is, of course, good in terms of parameters. And of course, it is very substantial in terms of numbers of stars observed. But I mean, we still need to demonstrate the strict compatibility of these two surveys, because what you really don't want is that you have two sets of benchmark stars which have a kind of shift or even more complicated behavior in between them. So what I'm saying is, yes, Lamoste, I think, has a very good potential as another set of stars, which of course is then advantageous in the sense that you will have nearly in every field a few of this. And, you know, the important thing is filters are very close in wavelength. So if you just, you know, circle ABC, 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 that means, you know, in short exposures of few minutes, you go, if you need to accumulate a proper signal to noise, maybe 2 or 3 cycles around, then of course you can filter out the atmospheric extinction to large degree. And what you need to determine is the, of course, shifts that will bring your instrumental magnitudes, which are very kindly provided by your system. Again, a very good presentation yesterday, to what will be calibrated magnitude. So in principle, you would need 1 star. In reality, it's much better to have 20. And yes, I mean, mostly we will have 20, at least when we include also Lamoste. And well, it's a kind of work in progress. At the moment, we don't use it, but I mean, in future, I believe we will, because even if there is a shift, this can be calibrated out, I believe.
Okay. Thank you. We have just time for a quick question via Alessandro Ederoclite. Yeah.
So, if I understood correctly your presentation, you are trying to get a very wide area. So I wonder how the use of JPass could help you, because it will also cover a wide area and also similar filters, and also will go deeper than the typical JPass observation. So I wonder whether your science could be done maybe with JPass as well.
Well, if I understood, you wonder what we will do about the faint targets, right?
No.
No, he said if the J, as you want a wide field, if the J plus wide field is enough, or if
No,
you
JPass.
sorry.
Yeah, I mean, the JAST80 field is perfect because we are speaking about, well, 2 degrees. Yes, I mean, this way you can, of course, as a mosaic, I mean, cover the thing in a reasonable number of exposures. And that's also, you know, there are 2, as I said, there are 2 advantages. One is very good observing conditions, and even more important is the fact that you can complete your survey of this rather huge field in reasonable time. Because you're having a large field of view. And so, yes, I mean, that's a definite huge advantage of JAST80. And there is no other telescope at this part of the Earth that would compete with it. I mean, so I think a big potential.
Okay, well, thank the speaker again. And the next speaker is Alessandro Ederoclite, talking about J-VAR, observing the variable sky in surface.
Thanks, Irene. Thanks to the organizers for having me here. I am the visible face of J-VAR to you today, but this proposal is on behalf of a variety of people. The co-PI of the project is Hector Vázquez Reunión, who's in the audience, and the core team is completed by Álvaro Álvarez Candal from Observatorio Nacional Rio de Janeiro, Beatriz Blanco Siffert, Universidade Federal de Rio de Janeiro, and Vinicius Morris Placco from Watt Lab, US. And the whole team is down here. Last week we had our first get together. You can see the shiny, happy faces of people getting excited about our project. So I don't think I really have to convince you that time domain astrophysics has had a huge impact on our understanding of the universe as is, starting from the Leavitt and Pickering 1912 to Mayor-Hello 1994, and the expansion of the universe, the accelerated expansion of the universe, and everything else that you can possibly imagine. Vast amount of ongoing projects are aimed at time domain astrophysics, and I'm referring to ZTF, Assassin, TESS, CHEOPS, the fifth incarnation of SDSS. And there's a vast amount of future projects, and possibly the most famous of those is the Large Survey of Space and Time. And we already heard about the Earth 2 telescope, we heard about Plato. And here I'm only speaking about optical. So don't get me started with multi-messenger astronomy, which was one of the key aspects of the Astro 2020 review, which came out a couple of weeks ago. So our main star is J+, right? We all love it. In this room, I guess 70% of the people are J+ members. It's the first generation survey with JST. We all know the 2 square degrees field of view, observing with the famous 12 filters. This is in the bottom right, you have the 2000 square degrees of data release 2. And here's just 5 random stars. The thing is, J+ and J pass don't have a time domain component. I just try to remind you of the importance of time domain astrophysics. So what are the variables? So we have the unique opportunity of doing astrophysics in real time with time domain astrophysics. And we want to use the strengths of the Hammond Auxiliary Survey Telescope, which basically are the wide field of view, good image quality, and its narrowband filters. Just for the fun of it, I put together the super famous detection of the variable by Hubble next to an entity one image taken by us with the 80. In fact, in a project which was looking for nova in entity one. Somehow in the back of our head, when we were thinking about J-VAR, I had these 3 things. So those of you who are familiar with the expansion of the universe likely remember the HST key project of H0. And here I'm presenting you one of the figures from one of the various papers by some collaborators using the C-fades to establish the type 1a supernova distance scale, and they were only using 12 epochs in almost a V filter. they were smartly separated. It was 12 epochs to get the period of sea fates. The rolling cadence of the supernova legacy survey done with the Canada-France-Hawaii telescope. This is a figure from a talk by Renard Peng. And the ones who are members of JPAS probably remember this spectral surface, which was taught by Enrique Xavier in 2004. And all of this somehow was in our head when we came up with the idea of J-VAR. So our idea is basically to use 3 broadband filters and 4 narrowband filters using non-photometric nights. In other words, if I can open the telescope, I'm happy. I'm the least popular person at SafeCat because we couldn't observe J+. And I was like, yay, but we could open the telescope. We use 11 epochs, which are separated by whenever the weather allows us. And this is crucial. Most of the projects, time domain, nowadays go like thousands of observations in a handful of filters, possibly 1 or 2. LSSTs are interesting exception to this. We observe in a given night, we observe at most 10, 15 square degrees. And we are happy to observe as little as 200 hours per year, which basically would give us complete time domain coverage of 54.8 square degrees per year. If you get confused by these 2 numbers, I can explain it later. So these are the, in upper right is the 7 filters that we have. So it's the it's our GRNI filters, broadband, and we have the 3 narrow bands, 515, 660, 816, and the 395. So in other words, it's the 6 most efficient filters plus the 395. This is an observing block as we do it. So we basically observe from the bluest to the reddest filter and a bit. We don't really care of the loss of efficiency of having to move the filter wheel too much, because it actually adds this time span of a few minutes. And we've been carrying this observation as open time proposal since 2017. So actually, we just hit the 4 years target. And in the lower right, you have the footprint that we have observed so far. But we observed in areas which have been observed by J+ already. So we can use J+ as our calibrator, as Carlinhos was suggesting it. Was here, right? As Jesus was suggesting yesterday. And this is the time differences between our observations. So, and you can see we sort of have a hole between 1 hour and 1 day time scale. Since we're observing under the footprint of J+, actually we are avoiding the plane of the Milky Way. And actually our field selection is a mix between being away from the Milky Way and being close to the ecliptic. So it's a little bit of a funny thing. It's a funny compromise. These are our exposure times with the magnitude limits by design and the magnitude limits that we managed to hit. And apart from the very red part, we basically hit what we expected at the beginning. Of course, you cannot. It is not trivial to go like to ask an exposure time calculator, compute me how the magnitudes are going to be like when it's cloudy, because that's not an exposure time calculator is designed to do. But what do we want to observe with this project? Speaking super fast. No. In a minute? Okay. Oh, okay. I'm speaking so fast. So I can slow down a bit. So what are our main science drivers? So our main legs are 3. main directions. So the first one is solar system objects, which is the reason why we try to observe as close to the ecliptic as possible. And the leader of this project, of this part, is Alessandro, and possibly the main person in this is Max Malke from Observatoire de Nice. And Max has provided us with an automatic system to identify any asteroids in our fields and to discover new ones. And through also the phenomenal work of Hector, we are basically discovering, we are almost discovering new asteroids almost on a weekly basis. And now we are on the point of being able to have our own photometric calibration, which is going to be important for what I'm going to say in a moment. And this is a figure that Alvaro made. If you compare the expected magnitudes from Skybot, which is a database of minor bodies, and you cross-match it with our detections, this is the distribution of magnitudes. And you can see we're basically able to detect asteroids all the way down to -20. Why is this interesting? Because actually, not only we can detect the asteroids, but since we observe standard filters, we're actually able to do taxonomy, and which is something I had no idea about before we started this project. And this is a figure from Morata and collaborators, 2021. And the whole spectral energy distribution here is from J+. But yeah, J+ is not aimed for variability, right? And but while we are, and we're actually able to, the marks here mark our filters. And you can actually see that this is a Vesta type asteroid, and we can actually nicely probe the whole spectral energy distribution of this. And if there's other type of asteroids, so and apparently the reddest part is the most critical. And again, not my field, I'm completely out of my comfort zone on this slide. And but this is something that we are very good at, and our data are basically unique on this topic. We can observe optical transients, and this part is mostly dedicated to supernovae, and this part is led by Beatriz Blanco-Sifter from Universidad Federal de Rio de Janeiro. And so far, out of the 100+ filters that we have completed, Bia and Luna Espinosa, a student from the University of Sao Paulo, they have analyzed 65 fields, and using differential photometry, which is honestly nowadays is the most promising technique for detection of transients, they have detected 10 supernova candidates, which we are supposed to report to the transient name service, 6 supernovae, which were already discovered by other surveys, and most importantly, from my perspective, 204 known variable stars and 211 not knowing previously variable star candidates. The joy of my heart, nevertheless, right, and this is, before I forget, this is a supernova in a galaxy at redshift 0.2 that Luna discovered a few months ago. Unfortunately, the nova exploded in 2019, so we cannot do spectroscopic follow-up. So we are now working on, instead of waiting for the field to be completed and analyze it, we're working on doing the analysis in real time, so that when we have these things, we can actually make a spectroscopic follow-up and basically become independent. The joy of my heart is J-VAR 28, which actually has this name, 2020 ADMB. I prefer to call it J-VAR 28. It was our first supernova detected by us, actually detected by Javier Hernandez, who's a database engineer of the UPAD, and he's the Hawkeye of SEFCA, and he basically was checking the images for fun, and he discovered J-VAR 28, and this is the light curve that Beatriz produced. because at that point we started to follow it up. The ZTF group confirmed it eventually with said machine to be a supernova 1A redshift 0104. Variable stars is perhaps the main core of J-VAR, hence the name. And this is mostly led by Hector and myself, and with the collaboration of Stelios, who's in this room, and Ramon, who's now sleeping because he's at the Observatorio Astrofísico de Jalambre, and Patricia Cruz, who I don't know if she's alive, and other people. So this is a pie plot that Hector did last week, and where we put together our detections and we cross-match them with the variable stars index, which is maintained by the American Association of Variable Stars Observers. And you can see which are the variable stars which are dominating our detections. And to at least my surprise, contact binaries are actually a big deal in here. I was actually expecting to have a little bit more eclipsing binaries. The beauty of this is you have a large variety, you can access lots of astrophysical topics, and these are just 3 light curves out of the thousands that we produce. And I just want to emphasize, so the lower right is a contact binary, but what really strikes me is the two variable stars, the Delta Scuti and the Ara Lyrae. You can actually see by eye how the temperature changes across the period, and this is just our observations. So without the need of anything else, we can actually do astrophysics as the period changes of any of these objects. Since we've been observing for some time already, we already have some idea of what we actually are going to discuss with the OAJ. So the project is highly modular, right? So 200 hours per year, we're happy. If we get more, it actually probably means that there's more cloudy at the observatory. So probably many people are not going to be happy. But if we get more, we're happy. If we get less, we're not particularly happy, but we can survive it. One field is 11 repetitions of 3 exposures in 7 filters, which basically gives you 231 exposures in any given field. We end up producing 700 gigabytes of data per year, considering raw data, reduced data, our own subtracted images, and the catalog. Of course, we're open to interact with the OAJ, especially in the case I screwed up the numbers, which could actually be the case. The J+ pipeline is serving us fantastic, and we have our own asteroid and supernova detection systems, which may be nice to include in the OAJ. The data is nowadays distributed to the collaboration within 24 hours from the observation. And this was something we had a little bit of discussion within the core team. We ended up agreeing on a proprietary period of 1 year. And we expect to have 1 data release per year. We are now designing the data release that we want to make next year. And the big deal, the big development is that we actually need an interface ad hoc, because we need to distribute these multicolor light curves, which are very much is what makes our project unique. To conclude, so J-VAR aims at being the time domain component of J+. So far, we've been running as an open time project, and I think Senaro was commenting yesterday that one of the key issues is to have the people to carry out the project. And this affected us significantly. At the beginning, this project was basically 2-3 people, and it took us time to engage the rest of the people and to actually get us moving, especially because I insist the data are unique. So we believe that now we are mature enough, both in terms of number of people and technical skills. We are happy to include new scientific skills and new scientific directions. So I thank you very much for your attention. Live long and observe J-VAR.
Any questions?
How strict are you guys with the selection of the fields? For example, you would be happy to share fields with other projects?
So Nacho is asking if we would be happy to share fields with other projects. So the short answer is yes. The long answer is we're not happy to change our strategy. So this observing block and its 11 repetitions are non-negotiable. Then we can put this in any place which I'm advancing something. This should be discussed with the core team, but I think we are happy to move this very much anywhere within the J+ footprint.
I was not thinking of changing the strategy of the observation, but I was thinking of making this observation in other fields that we would, for example, the ones that we were presenting, where we are going to take very deep exposure. So whether you can do also this kind of analysis with your strategies and support, but in fields that we are going to, for example, do very deep, so you have such very deep data to make a, let's say, comparison or variability with respect to the information that. So I was just thinking on this kind of thing.
So yeah, Nacho was considering if we could do basically J-VAR on top of pointings like the project that he's proposing. And again, I insist, this is something that I should discuss with the core team. I believe it would be doable.
So thanks, Alex, for this nice talk. In terms of data, let's say data distribution, what would be the highest science level products that work out, like about the life curves or the property?
So Andres is asking what are the highest data products that we are planning on delivering. If it's just the light curves or typification of variables, periods, I guess.
By the way, that's clarified. Just provided the light curves.
And he's clarifying that just delivering the light curves would be amazing. So yes, the light curves is the most basic thing. We are still designing the data release one. I think I can anticipate that we want to be able to provide typification of variables. Not sure, I would guess periods. And I think for a supernova, we are considering typifying also the supernova. I don't remember if we agreed on something about mind bodies. Sorry.
Yeah, no, we have another question from here. So it's
Sylvia, I think you can unmute yourself.
yeah.
Hello.
Yeah.
Yeah, I don't know if you can see. Anyway, can you hear me?
Yes, loud and clear.
Yeah, thanks. Actually, it was connected to the question that Nacho about the pointing on the same fields. I wanted to ask Nacho yesterday. Maybe he mentioned, but I missed it. Actually, how are they targeting the fields? I understand they have to be nearby galaxies, but is there some criteria on choosing the targets, like a morphological distribution, or I don't know? What is the criteria to choosing the galaxy?
I think you better move here.
Yeah.
Okay, so there is no selection yet. So we will decide on the basis of the low galactic extinction, the velocities of the objects, but the idea is to try targeting different masses and different morphological types. So we expect around 20-25 objects. So we will try to select the fields to maximize the number of galaxies and the different properties of the galaxies. So the main selection would be low galactic extinction to avoid many contamination by galactic cirrus.
All right, thanks.
Thank you, Alex. Yeah, and the next and final speaker is Gonzalo, talking about MULTIEPOch disparity examination of H-alpha and impact on MUDEHaR.
Okay, thank you. So, hello everyone. My name is Gonzalo Holgado. First, I want to thank the organizers for allowing me to give you this talk. This is my first not virtual talk in 2 years, as many people. And thanks again for the organizer for this and everybody for. So today I want to talk about MUDEHaR. What is it? And what we want to do with it. I'm just the representation of the MUDEHaR team, and what we want to do with it. So first, MUDEHaR is a unique and beautiful characteristic architecture of the well. You should see, but also is the acronym of the MULTIEPOch disparity examination of H-alpha and infrared, which means that this is a planned observational project which is focused on the multi-epoch observation in 2 narrow filters, H-alpha and the Gaussian triplet window, planned for the T80 telescope, focusing on obtaining 100 epochs for 20 selected fields, measuring variability on different scales for the tens of thousands of stars in each field, and making use of the reduction strategy and pipeline of Galante, which is a previous observational project here in the J-80 telescope from the years 2016 to 2021. Galante will also be used as the calibration system. So that's the summary, but to give a little bit of scientific context, I searched for observational photometric surveys, including H-alpha. There are many. For example, EGAPS, a combination of IFAS, UVEX, BFAS is a very strong one. G+ and S+ itself contain H-alpha narrow filters, and omega wide. I include this omega wide last one because it's the only one that focuses on the multi-epoch aspect, the same as MUDEHaR. So, and omega wide is in the south. So we think that the MUDEHaR defining and unique characteristics are the combination of the multi-epoch nature, focusing on the galactic disk with a very extensive dynamic range, and also with the powerful resolution of the T80 telescope. So these characteristics are aligned with the main observational project for us, which is well, in itself is also aligned with the Galante goal, because Galante is providing the massive stars in each field, and MUDEHaR will monitor those stars to find peculiar objects. Those that are variable because of magnetic fields, disk emissions. This is related with the OE and the stars, Lipschitz binaries, and so on. These are interesting because these are very rare objects, and we are trying to understand the formation of the massive stars. But also, this is only for the observation of massive stars. But MUDEHaR is observing the whole field, and we will be able to obtain a catalog of the tens of thousands of variable stars in each field. We consider that the unique characteristic of the T80 telescope and our expertise acquired with the Galante project are a unique opportunity, also focusing on the multi-epoch, as Alessandro has told us. As for the For the layout, we pre-select well-known star-forming regions in the galactic disk with plenty of complementary data. And those are already observed and reduced in Galante. These are the Galante images from Cygnus, from the Pleiades, Zeta Nebula, Orion, North American Nebula, and the Pac-Man star nebula. And focusing on the filter system and the observing strategy, we are talking about two narrow band filters that are in the standard G+ filter wheel. One is 660, which is on top of the H-alpha line, a main diagnostic line for stellar activity. And the filter H61, which is on top of the calcium triple window that we will use to tie our MUDEHaR photometry to the astrometry and photometry of Tomaz and Haibo. As for the observing strategy, we are thinking about 100 epochs for each field, for each star, in the two filters, and we try to cover the variability in the hours, days, and month scales, focusing on the peak of the visibility window of each field. That's almost 10 weeks, and then repeat the next year again. For a summary, this will mean the total amount of hours observed in each year. This is the exposure times are 4, and we will include ultra short exposure times for those fields, including very, very bright objects. This makes a total of 200 hours in 1 year, including overheads. So we think that our observations are very independent of the observational conditions. Full moon nights are not a problem for us. We think that in the peak of the visibility window on each field, we will like for 1 field per night. We consider it could be feasible. If you observe less, we can exclude the science, it has less epochs. We're focusing on the right ascension that is complementary to G+ and others of the projects that are presented here. That's considered another plus in some places. And as I said, these are G+ standard filter wheels, so no necessity to change the filter wheel. And the data reduction, the pipeline, the storage, and the data provided in a web page is already constructed by the Galante team. Our time schedule will include the generation of we consider that we are well versed in the working package of generation of annual proposal and annual reviews, because we have been already doing this with the Galante project. In terms of the data download and processing, we are already working in full capability, because Galante pipeline is working. For example, 3 weeks ago, we received the last batch of the Galante observation, and these are already the reduced images. And in fact, we have been already finding variability in substars. This is because some Galante fields have been repeated for many reasons. And this is just one star in H-alpha that have a variability in H-alpha of 1.3 magnitudes. This is a high proper motion star with an unknown origin of the variability. And in terms of the schedule of the publications, we are considering to attach following the Galante schedule of publications. So just complementing the Galante publications with the MUDEHaR inclusion of the variability and the selection of interesting candidates on variable stars. So that's the MUDEHaR observational project. Now I want to talk about what we can do with it. So our principal objective is the identification of massive stars with variability in the observed fields. That includes, for example, magnetic OB stars. These are interesting because only 10 to 20% of OB stars are magnetic, and the origin of the magnetic field is still debated. So to increase the sample we consider that is crucial. There has been effort in tying the photometric variability with the magnetic fields, with, for example, depending on the wind structure following the magnetic field, you can find different types of variability in magnitude. And this is the model, and it has been found also in the observation. In fact, I'm in the MULTiepoch collaboration, identifying magnetic O stars with the test photometry. We have already have results, but we are quite limited by the resolution of the test. Something that MUDEHaR could help with. So in fact, we are already working on each step that will provide us with additional magnetic stars, because to increase the sample, you first need to find candidates. That's what Galante is doing. With a combination of the TAT observations and via photometry, we are able to detect new O candidates and B candidates. Then the MULTiepoch photometry will be done with MUDEHaR. Then you need to use you need to differentiate between different modulations, between the magnetic modulation or other types of modulation with the long Holgado periodogram analysis. And for that, you need a very good rotational known of the modulation of the rotational properties, and that's something that already have been working myself with the determination of the BSNI of a large number of O-type stars. So we have that covered. But the last step is the analysis with an ADM, the analytical dynamical magnetosphere, and that's something that I will need help with, but I'm in the MULTiepoch collaboration for that. So that's for magnetic star, but other type of variable star that we will find and will help us to give us interesting additional constraints will be, for example, eclipsing binaries that help us with the additional properties of binaries information. Also, the OE and BE stars that are related with variability by the disk emission. OE and BE stars are related with the very rapid rotation and the formation of the disk. That's also related with the rotational projected investigation that I speak before. And finally, it is known that stochastic variability could be related to internal gravity waves, something that MULTiepoch is also working on. Okay, that's for massive star. That's my topic, but the MUDEHaR teams is also interested in using some other types of variable stars that MUDEHaR could find. For example, LBVs, long-density variables, some biotic stars, an active M star that's separated from the non-active M stars by the pseudo equivalent width in H alpha. But we consider that the level of photometry accuracy that this narrow band H alpha provide will help us also to find this type of active M star and separate it from the non-active M star. And that was fast. To wrap up, this is MUDEHaR in a nutshell. Again, we are planning, this is a plan for the MULTiepoch observation of 20 fields, around 40 square degrees, focusing on the galactic plane with different exposure time to maximize the dynamical range, and focusing us in the determination of massive stars with variability, so peculiar massive stars, but also with the idea to provide a legacy value of a catalog of thousands of variable stars of all types, and also the possibility to map the variability in the sky for H alpha and the infrared filter. And that's all. Thank you very much.
So we have time for questions.
Yeah, are you considering to look for H alpha shells around those stars?
Martin has asked if we are considering to search for shells around H alpha shells, right? Yeah, so I know that people in the has worked on the topic of finding identification of picture identification of bow shocks and so on. But I think that no, H alpha bubbles, not particularly. Yeah, but it could be fun.
Yeah, because the exposure that you are requesting, like 200 times 50 seconds, shows a hallucination around all the stars, maybe work stars, but also LEDs, symbiotic stars too.
Yeah, symbiotic star was already told to me that there is possibility, but the other that you have speak about, so some bubbles around different kind of objects, we know, but we are right now a small team, but we are open. Okay.
So yeah, I can ask you a question. So regarding the nights, as J-VAR uses non-photometric nights, you will be also.
Yes. We consider that there is very little limitation for this kind of objects. In fact, we are trying to focus on the bright objects that other H alpha photometric studies tend to ignore because they saturate. So we will get we'll try to get up to magnitude 3. These massive stars those kind of in the sky.
Yeah. Hi, you can open your mic and ask the question.
Okay, thank you, Gonzalo. Okay, can you hear me?
Yes. Hello.
Okay. Well, congratulations for your talk, have been very nice. And so my question is about the WR, the World Rayet Stars. Do you have any prediction of the expected number to be discovered with this new survey?
Well, in particular, that will be related to Galante. Galante will be the finder of World Rayet stars. These are much less square degrees, 40 square degrees. So I think that we are able to identify them with the TAT observation combination of the filters, but that will be more a Galante project.
Okay, thank you. So it's not expected to get farther than Galante in this aspect?
No. In fact, it's more, well, it's like a complementary work on the Galante data, because we need Galante for the calibration, because J plus it doesn't get to this right extension.
Okay, thank you, Gonzalo.
Thank you.
Yeah, I don't know if you mentioned, but what is the expected total integration time that you have for this?
Yeah, it's 20% less than 200 hours. So yeah, because the overheads were considered that. So this will be for each year. We make like for each field is like 5 epochs in 1 second, 5 epochs in 10 seconds, 5 epochs in 50 seconds or 100. No, sorry, 50, and other with 50. Because we need 2 different air masses. Yep. Okay.
Okay, then we'll thank Gonzalo. So before the coffee break, I think we are taking the picture. Yeah, besides just where should we go? We can go downstairs.
Then the
yeah, okay. Yeah, so we'll be here for the discussion at 11:30. See you then.
asking about what about them? I can make a screen capture here.
Okay, we'll think about it.
We have to leave the other one. Take a screenshot of Can you open your camera so I can? Where is the?
Yeah, where is the video?
Maybe you can stop sharing.
Yeah. And now gallery view. Okay. Open your camera. We can be here. There we are.
And we don't have the mask. We don't need the mask.
Can you hear us now?
Oh, yes. Yes. Okay.
Okay.
So the idea is to wrap up a little bit what we have seen during this day and a half of presentations, and then leave some time to discuss, freely discuss and exchange ideas, and send questions or whatever we consider is necessary. So just summarizing for everybody to be clear, the CEFCA is going to open a call for proposals for second generation surveys with the T80. These are long surveys, so the amount of time that we are offering is 3,250 hours spread all over 5 years. So we expect to receive project surveys with that length, 5 years. The minimum amount of time per project is about, I mean, those things are preliminary, right? We need to figure out the final details of the call for proposals, but I don't expect that the final proposal to be too different from that. So we expect project to request from between 200 and 650 hours per year, and CEFCA is guaranteeing the observation of a minimum of 75% of the allocated time. So this is going to be the new open time mode for the T80, in the sense that starting in 2023, the T80 telescope, the T80 is how we familiarly tell the telescope, the Hubble Auxiliary Survey Telescope, is going to be used to continue with J+ observations. It will execute the allocated or the awarded second generation surveys, and it will also observe targets of opportunity, but no regular, in a semester basis, call for proposals will be released. So this is being substituted by the long surveys. So we are not having any regular programs or large programs, in the sense we are having, we have been offering between 2016 and 2022, right? So this is a change. It's not an addition, but a change. So now we are focusing on what we think the telescope is much more powerful, which is executing surveys. And this is the whole thing about this meeting, right? We are working now to figure out the best use possible for the telescope and the best science, identify the best science. So having said that, and taking a look to the presentations that have been presented these days, if all the presentations or the projects that have been shown go to the final call for proposals, we are expecting or we would have like an oversubscription factor of about 3. So I think this is a success. That means that there's a lot of interest in this new phase for the DAD. But at the same time, it means that we expect to have some pressure. So again, this is just for you to encourage to figure out the best proposals possible. And this is based on what we have seen those 2 days. I have to say that the call for proposals and this meeting are kind of independent processes. In other words, it doesn't mean that only the projects that have been presented here will be allowed in the call for proposals. It may happen that a different project appears and then it sends a proposal at the last minute. Or not all the projects that we have been seen here are forced to present a formal request of time in the proposal. So this is the letters of intent process, and this meeting gives us the opportunity to work from the very early stages with the people, the groups that are interested in these large surveys, to work together and end up presenting the best proposals possible. And this is the whole thing, right? But it is not closed. So if you know from somebody else that is not aware of these things that we are doing and maybe interested, I mean, they may end up submitting an additional proposal. Also, I think it's interesting, based on what we have seen, that about 75% of the time is being requested for Milky Way science, and about 25% of the time for extragalactic science, which kind of makes sense, right, for the type of telescope that we are offering. Also interesting that there is a significant oversubscription for dark time. So remember that we are offering dark, gray, and bright time in a fraction of 1 to 1. But what we are seeing here is a significant amount of the projects, or the time required by the projects, that will need dark time. This is, we need to be aware of that, because the pressure on dark time will be much higher than, for instance, in bright time, as on the other side is expected, right? So I think it's interesting for you to just to think about what part of the project, or what is the impact on your projects if instead of dark time we use gray time, for instance, right?
But if you allow me for
yeah, so sure.
In a QMO telescope, dark and gray and light, not too much into that, because you can consider dark and bright time, because the gray, gray nights can be split in dark and bright. So having the moon out or having the moon down. So the principle is like half dark, half bright. No?
This is not completely true, because when you have, if you have full moon, either you have full moon is bright, or the moon is not above the horizon yet and it's dark. But when you have 50% of the moon, part of depending on the region of the sky and how far you are from the moon, may be considered as gray. So this is the way we are operating. I don't know if you want to comment on it, or something more about that.
Yes, my comment would be that I understand what you said. So we classify roughly the nights as dark, gray, and bright in a proportion of 1:2. So in principle, it's true that during gray time, part of those nights, when moon is down, could be considered okay for your program, but we label those nights as gray. So maybe here the point is to clarify this definition of that.
But my point is that I would talk more in terms of, instead of nights, hours. You can talk about dark hours, bright hours.
That time.
In that sense, because it's a QMO telescope.
So
you don't really care about night, but hours.
Yeah, you are completely right. Dark time, bright time, or hours. Yeah, you're right. Okay, so also we have seen that many of the projects that have been presented are making use of J+ filters, but there are some projects that are proposing the manufacture of new filters or the use of J+ filters, so filters that are different from J+. For the J+ filters, the filters are manufactured, as has been discussed, the filter wheel that can integrate them. But for the new filters, also maybe interesting for you to think about that is there is a project proposing, like for instance, MUDEHaR, proposing a set of filters around the H-alpha line. Would, in the case that this project goes further, so is approved and the filters are manufactured, would those filters be useful for your science or better than the ones that are in J+, but you have not considered because you said, okay, I prefer not to manufacture and go for the ones that already exist. So this is something that also can be discussed or can be thought, right? There is an uncertainty there because at the end, we won't know if for instance, the MUDEHaR filters will be manufactured until the time allocation committee makes a decision, right? But I think this is worth to have this idea in mind. And also, there's the other filter around the calcium line, very, very narrow, apart from the ones around the H-alpha. So same thing. So just think about possible synergies or collaborations to reinforce the need of the filters or the strength of the proposals and so on, right? So same comment for the kind of observations. We have seen today that for some of the projects may make sense to share some of the pointings, right? You were commenting today that, okay, we have pointings in the halving project where we are going very, very deep in looking for nebula, extended nebula. So would it make sense to use some of the pointings in the MUDEHaR project? So there is an added value to the science that can be acquired there. So these are kind of synergies I think we can discuss today and in the following weeks, right? So I think that's also interesting to find out ways to optimize the access to the telescope and of course to reinforce the return of the projects that are being presented. I'm just throwing out a few ideas, and then we can just open a table just to discuss. And of course, synergies scientifically speaking. So synergies from the scientific goals of the different projects. We have seen here projects that are similar from the scientific goals point of view. So would it make sense to just unite forces, to join efforts, and instead of having several projects with common scientific interests to work out in a single project that is much more strong, so increases the possibilities of being awarded with time? Again, something to be discussed. Of course, at the end, the decision relies on the PIs of the projects. There is no doubt about that. We just want to make you think about ways to improve the strength of the proposal. And just to finish this longer than expected introduction, so also was commented yesterday, there is a possibility to maintain meetings with projects that are considering different synergies. So I think it's good to have meetings apart from the one that we're having today in the following weeks, previous to the formal call proposals. CEFCA can also participate if we can support in any aspect, or meetings with individual projects just to figure out the details of the observational strategy, the feasibility of the manufacture of this very narrow band filter, or whatever thing where CEFCA can support, can provide the deep expertise on the telescope, the instrument, and the observing conditions and observational strategy based on the experience that we have had in the last few years. So just let us know, and we will be happy to, not happy, more than happy. We are encouraging you to have those meetings so we can reinforce the proposals, as this is the whole point about that. Right? And in that context, just was mentioned yesterday, but to remind that the call for proposals is expected to be open in February next year. So if you are thinking about having those meetings during the proposal preparation, it would be good to have them. December is a difficult month, but probably second half of January, February, so prior to the proposal, so we have time enough to tie up all the details and improve all the strategies and return. And that's it. I mean, this is more or less the ideas we think is worthy to discuss today. I don't know if you want to complement what I said.
Yeah, for example, one interesting thing about the project, I think that regarding there are several projects that are using J+ filters. There are 3 that are targeting basically chemistry of stars. It's this about the Milky Way streams, the Earth 2.0, and the Zwitter at the end. So there are different goals in some cases, but they are targeting the chemistry of stars. So that is telling you that with large field and with the filters, narrow filters, this is one unique thing that you can do. Also, there were a couple of projects that are asking about variability in some cells. It's J-VAR, MUDEHaR, and also MULtiepoch is also involving some variability. Again, you have large field, and you can have a lot of stars, a lot of sources with variability in only one shot. And with the narrow filter, you can do interesting science, targeting activity lines, as we already saw. And then there are also the 2 projects that are looking for this low surface brightness at the end, from Nacho and Halfi, that are in different contexts, but they are looking for the low surface brightness profile. Again, with a large field of view, you can do a more efficient way. You can go deeper because the observational strategy and the different pattern and other things make you capable with a small telescope to go very deep. Because this is also very interesting. And I think that these are the 3 big blocks that I saw in this project. So yeah.
There is a question by Simon Daflon. Will the observations of these 2nd generation surveys impose any impact on the observations of J+?
In principle, as far as I understand, there is not going to be impact on that. So in principle, they are going to coexist. And with the time that is being offered, there is not going to be, in principle, problems. So, of course, in dark night, perhaps there are more pressure, and they plus have to observe less time than up to now, but in principle, it's something that is not going to erase T+. T+ is going to continue gathering data. That's it.
Another person with wires. So, Francisco.
You can unmute yourself and
talk.
Me?
Yep.
Okay. I have an open question maybe for Haibo, for Tomaz, and also for Gonzalo. And it's concerning this synergy between the projects and Gaia. And thinking in this idea that we are thinking in a survey for 2023 to 2028, thinking that maybe in 2026 they will be probably, we hope, the 4th release of Gaia with all the amount of low resolution spectra for hundreds of millions of sources. If you have this low resolution spectra, at this moment you can make some synthetic photometry, and you will have in one moment epoch spectra. For example, for Gonzalo, the question is how this epoch spectra for the sources you are interested in to analyze in this concept of time domain analysis. Can you think in which part of the data or the analysis of the physical or the goals you want to attach, they in some sense can be also done using Gaia data, applying to this spectrophotometry the synthetic photometry? Is the too low signal to noise of Gaia the fact that imposed to have another observations here with G+, etc., just to balance this idea? No? The same happens with Tomaz in the sense that, for example, excellent this need of spectroscopy. Could the RVS stars that we are publishing now in year 3 in May or June 2022 be used as benchmark stars, in the sense that you are talking about an H and K line in the calcium line at 394, but maybe there is the other analysis in the 861, so in the calcium triplet in the infrared. So just thinking in this mixture between one thing and another, if you can give me your thoughts on that, your ideas of what kind of link, because it's great to have this link and to have G+, the T80 just at the top of the analysis, thinking in the data.
Maybe if you allow me to share some thoughts, because I'm also involved in Gaia.
Yeah.
Yes, you're right. Around 2026, there will be the next data released after the one which will be next year. It is of course difficult to predict, and actually it's not decided what will be exactly in this data release. But it is definite that 226 cannot be the last data release of Gaia, because if you think there will be fuel till beginning or middle of 225, and certainly you will not have it 1 year later. So I think that I will be well retired. It will be 28 or 29 or something like that, that you will have a final release of Gaia. That's perhaps the realistic schedule. And I mean, I would now suspect, of course I do not know, but I would suspect that really this whole body of data, of course, this belongs to the final data release. Because, before that, of course, the question is, are you calibrating well enough that you are courageous enough to really release the epoch data? So I think that this will come, as a progress. Quite possibly there will be averaged BPRP spectrophotometry. But the question about the epoch one means that, we should be then sure about all the calibration final ones. And I would think that maybe this will not be 26. We will see. Okay, anyway, this is a kind of rough prediction. Nobody knows, actually. Also Gaia people, nobody knows. Everybody working hard, but we will see what happens. Then about the signals. Yes, you're right. BP and RP is spectrophotometry. We are speaking about a certain degree of, let's call it full width half maximum. And this is of the order, let's say, 2 worse than what you have by J filters on our telescope here. So somehow it is not the same thing. Also, you need to note that, yes, in the end, adding will add signal, because there will be so many epochs, of course. So for unvariable objects, this could be an option to have a very good spectral distribution, But there is a trick, and the trick is that, as I said, if you look, I think it is in the Brusty 2016 paper, if I remember well, there is a figure about relative sensitivity versus wavelength for the BP and RP. And yes, it has a dip around calcium H and K. So this is actually the combination of 2 reasons is why we went for it. One is this is by far the strongest signal. Of course, you have something else, and you have a picture of the week in Gaia for giants. You can go to the magnesium triplet at 516 or whatever it is, the wavelength. And this has some signal, quite a bit weaker than HK, but still has some. And yes, in principle, this could be the source for the alpha for giants. At least when I check that, I don't see this in dwarfs. I checked it in synthetic spectra, not in the Gaia ones. So there is some hope that for the brighter stars, looks like, according to this picture of the week, Andreas Korn and this kind of guys from CU8 are there. They say we are speaking about bright and relatively nearby giants, of course. And so, yes, there will be some reach on alpha, but for selected stars only. Actually, quite a bit brighter than what you can do with JAST80, And then a comment whether can you, of course, calcium is the alpha element. can you use instead of calcium H and K the calcium infrared triplet at 860? Well, this is being tried, and actually I can tell you that people are very happy about the spectra that Gaia is producing. But of course, we are speaking here about magnitude 12, maybe in some lucky cases 13, and of the order of 14 to 15 is the limit for the radial velocity. So not for the spectroscopic parameters, but for the radial velocity. Of course, it's much easier to judge the temperature, but if you want to go with chemistry, it's a bit tricky. And the reason I know is because with RAVE, we were observing exactly the same wavelength range. And I can tell you that, well, just to make it a kind of light talk, Amina Helmi, which we all know and respect very well, well, she was pushing for years, Tomaz, we need alpha and we need iron abundances from RAVE. And I kept saying, yes, but unfortunately, they're hopelessly degenerate. I mean, it was a kind of fight of 6, 7, 8 years. In the last 2-3 years, with some people in Potsdam, we somehow managed to some degree, I mean, separate these two issues. But still, I mean, you need relatively good signal to noise, and Gaia will be getting this only for very bright stars. So I would say that some information on chemistry, yes, but roughly till magnitude 13, and separation of alpha and iron, very difficult unless you're having quite a bit brighter objects. And there, of course, consider now the number of spectroscopic surveys which are coming in the plane. I mean, this decade is really the decade of fiber multiplex surveys. So I think that this will be to some degree done also from the ground, I mean, for these bright stars. So in a way, yes, there is this space, and there are good reasons why to go to calcium H and K, just because of the strength of the signal, and because it is complementary to Gaia in this sense. I mean, so in the very end, of course, we will use everything together. That's, as always in astronomy, everything is free and everything is publicly available. So there is ground for doing that. I mean, and it's not only the fact that Gaia perhaps will be published later, it's also legacy value, I mean, which I think will stay. Also, you can, of course, do it yourself, a quick calculation. Gaia is fantastic in every respect. But one thing which I normally skip over when speaking, and of course putting Gaia as really a revolution, is how big is the mirror. I mean, Gaia is a small telescope, if you think about it. I mean, and of course, everything is self-calibrated. People are really working hard, and it's a miracle what comes out. But I mean, still, just 80 is order larger, I mean, in the sense of what you can do, and you have pretty good observing conditions. So yes, Gaia has no atmosphere, but you have a good one. So somehow, in a way, yeah, it's if it comes to signal to noise, and when measuring narrow band, it comes to this thing, it's a problem. And well, we will see. I mean, we will also see in data release 3, calibration of Gaia, of course, is not trivial. So we will see to which degree we have it next year. I mean, but anyway, I think that the time allocation committee will actually get the proposals roughly at the time of Gaia data release 3, and they will judge it when this will be already around for a month or 2. And so somehow the time allocation committee can, well, judge the proposals also on this. I mean, because they know that the next big data release is several years later, right?
I fully agree. I fully agree with all your comments. It's just the idea that we are exactly in the same schedule, no? In some sense that all the data will be there, no? Right. From this point of view, I fully agree that, for example, I have used the J+ filters to analyze this ultraviolet signal for the high velocity stars looking for Enceladus, Gaia Enceladus, and so on. And it's great to have these G+ filters at the level of 395 or something like that. So great. I fully agree. But it was something that we have to think in the idea that we are just working together.
Yeah, for sure. I mean, a strategy when you would say, well, we should be faster than Gaia and we will take the cream, that's a wrong one. Because certainly you can wait a year or two more, I mean, and get possibly better results. So somehow we need to be complementary and we need to have a kind of synergy.
Okay, Mohammed?
Yeah, should I add something? Yeah, because... Hello, Gonzalo here, can you hear me? Francesca, Tomaz?
Maybe you can come a bit near to the microphone for me and for the people that is there. I don't know.
Yeah, yeah.
Going.
Wait a second.
Yes, sorry. Better. Better. Can you hear?
Yep.
Okay.
Perfect.
So, yes, I won't add nothing to what Tomaz says. I can't. But just my experience with, for example, with Galante, was with what Gaia is already giving us is fantastic. Is amazing. In fact, using differences between the DR2 and the EDR3, we are we're implementing our calibration of the ultraviolet, well, the U filter, the 348 in the G+. So it's already a fantastic data. For MUDEHaR, well, we think that the only problem is that the clustering and the crowding could be less powerful than in what we can do in MUDEHaR. So on top of that, the different.
Sorry, the sound went away.
We have lost the sound.
Maybe now?
Yeah.
Okay.
Yeah.
So to very quickly wrap up, Gaia data already is fantastic. It's helping us with photometry and photometric calibration. And with MUDEHaR, we think that it could have some issues with the clustering and the bright stars.
Yeah, certainly. I mean, in Gaia, clustering can always be a problem. Well, if I just go back to I think DR2, we realize that we have something like, if I remember well, 57 stars which are closer than Proxima Centauri, and of course none of them is real, and all of them are in overcrowded regions. So somehow, yes, crowding in globulars, also in Bada window and so on can be a problem, and also to some degree, as you know, Gaia is limited in the data transfer rate. And therefore, when you are pointing to really Milky Way plane, hopefully the data come down, but occasionally it may happen that some of them are dropped. I mean, I think it is not a major problem, but every user should be very much aware of that. And yes, I very much appreciate that you are doing the astrometry of the CCD frames based on Gaia, because then we know in which system we are. So that's great.
Yeah, that's exactly what Galante is finding. Yeah.
Exactly.
Can you hear me? Okay. So Tony, my question was about the construction. Yeah. Okay, can I speak now? Yes. Okay, so it's about the construction of the filter wheels. So you said it's possible to add the new filter wheels if necessary for more like JPass filters if you want more than just the 7 that are provided. Is that does that take long, and how much will it cost? I mean, if in a project we want to add more filter wheels.
Yeah, I don't have an answer for that right now because my memory for long-term projects is limited. So, but I have that information for sure. I can look for the information, but I don't have this number right now. It is true true that we have the designs, of course, we can manufacture. It doesn't take that much, that long. So in the time scale we are talking, it wouldn't be an issue at all. But regarding the cost, I'm sorry, we can discuss that later once I check my files, but I don't have the number. It is not that much. So features are not features. Features in themselves require more time and also more, not the feature.
One other small question.
Not the proprietary period expected for the high-level science. So is DEFCA going to be producing the low-level, like UPAD is probably going to be producing the low-level reduction. But what are the projects expected to have a certain proprietary period, or can the project, is that up to the project themselves?
Again, this is also an interesting question. This is not defined yet. So regarding the proprietary period, what I can say is that the proprietary period that we have been applying for the regular course of proposals that we have been offering since 2016 to 2023. And this is 1 year. But we are now talking about long-term surveys. So depending on the science and the kind of survey, it may not make sense at all to have a 1 year proprietary period, because if the survey requires more data acquisition before the first science can be released and be obtained, 1 year seems too short, right? So this is something that we need to discuss internally, and it could happen that at the end it is going to be analyzed project by project basis, right? Because there's some aspects to take into account before defining the proprietary period. And as far as I know, this is something we discussed. I don't know if somebody wants to add anything regarding that regard, but
I think that one of the things that should be provided probably is data release idea, or at least a plan or action plan. So that also can help to define different proprietary periods. In the sense that if you are going to release, for example, high products of the survey, it makes no sense that the raw data are private, but you are already releasing basically the difficult things. So it makes sense that, for example, in that moment, you already make public the raw data, for example, if not in advance. But at least in that moment, it does make sense. But when you say that, that is something that can be discussed in a project by project basis, also taking into account the different goals and the different strategies.
I have two questions. In fact, one is for Jessica and one is for Tony. So the one for Jessica is probably the most complex, perhaps. In Gaia DR3, there's going to be the variability, the release of the data with the variability. Is that only the magnitudes, or also the spectra, the various different epochs of the spectra? I'm not sure if
I don't know if I can answer you. The idea is that everything that can be said at the moment is in the Gaia webpage data release scenario. So this is what is there. What we can say, it's where maybe Thomas knows better than I, but everything is there detailed. What we can say, what is clear is that the processing is going very well for DR3. Everything is on time. And everything we can say is that what is in the Gaia release scenario. I can send you the link. Okay, Juan. I send you the link now. We cannot hear you now.
An interesting point. If there is a strong argument to delay the end of the release of the tender process, this is something we can evaluate, but we need to be aware of the price that we are paying. It may impact on delaying some of the projects, in particular those that require new filters, and we are adding risk in the design, the survey strategy implementation, because the amount of time that will be pending or remaining is lower. So if there is a strong argument, this is something we can consider. So at the end, it's also open, right?
Martin?
Yeah, I have one technical question and also an open question on a possible synergy. The technical question, we have been talking about the possibility to implement the auto-guiding system, which is already there but hasn't been never mounted on the telescope and tested. But there were, as I understood, there were some risks that even this auto-guiding system is not going to provide good results, as it is not using the same optics as the camera. Can you have some assessment of what's the possible success of using the auto-guiding?
Okay, so I want to just to correct a little bit. So the lack of functionality of some of the auto-guiding systems that were conceived at the very beginning of the project is due to the fact that the camera is in one of the focus of the telescope, and the auto-guiding was initially conceived as a piggyback telescope mounted on the structure. So differential fractures make that auto-guiding system not to be reliable. Yeah. So then in that respect, we design and manufacture but not deployed an auto-guiding system that is installed as part of the camera. Okay. So that in theory shouldn't have those problems. So this auto-guiding, once commissioned, should be reliable, right? It has some disadvantages, like for instance, is vignetting is likely one of the sides of the CCD, because I show the field of view of the telescope and the size of the CCD. There is no room, physical room, just to put a pickup mirror there and start light from the same focal plane to this auto-guiding camera. So there is that price that we would be paying. But once commissioned, this should be reliable, but there is an uncertainty on the time required to perform that commission, because it is designed and manufactured from the optomechanical point of view, but the control system has to be developed. So there's a significant time and effort that is still pending to have this auto-guiding working. As well mentioned yesterday, at the end, it has not been done because it has not considered to be necessary. Up to now, given the science and the typical exposure times that the telescope is working with. But if your project requires longer exposure times, this is a possibility. But as mentioned, that implies that certainly implies that the project won't start in 2023-8. It will be started later once the auto-guiding system is commissioned and is made functional.
Okay, yeah. Certainly, this is something that we need to discuss with other people.
Sure thing. Can I ask you, when do you need longer exposure?
Well, if you go to longer exposure, you are going to get deeper.
Because of the rig noise?
Yeah.
But here it's extremely small. I understand.
It's 3.3, 3.4 electrons. Yeah, because the very low expressions that we have.
But in practice, what it really kills the low supervised projects, not necessarily the read noise, but the artifacts connected to the flat field.
Yeah.
So in that sense, you really would like to have as many images as possible.
Yeah,
so
so
value to compensate the
yeah. So there's a trade-off between the two. Exactly.
You do the flat field with your own data. As soon as you guarantee that you are going deep enough to observe the sky in the way that you are observing, because you're using analog filters. Yeah. Then the larger the number of exposure you can do during that night, the better for you to correct it.
Yeah, so maybe because I am observing the narrow filter, I may want to use bright time to get a deeper larger background or something like that. It's really
you need to make the number.
Yeah, I need to make the number. Yeah, my other question was I learned about the MUDEHaR project and I found it very interesting. I was talking to Gonzalo and he let me know that in the Galante project they had not found any of those circumstellar medium emission around those stars. But I wonder whether they have some diffuse H-alpha emission, which is going to hinder the detection. So maybe adding to this project or to some of the stars in this project, some observation, let's say the oxygen 3 emission line is going to be able to distinguish this emission from the circumstellar medium, and the one which is really coming from the stars. Talk about this.
Yes, yes. Yeah, I think that would be interesting because, as I said, the photometry from Galante is done, and I think that including this filter will have this information, and it's not so far away. This will be a J-VAR filter. Well, there is some jetting, as everybody already know, but it could be possible to do the spectrophotometry and the calibration of this.
Yeah, I think that if you add maybe something like 30 minutes or maybe not even longer than 1 hour, oxygen 3 for the total exposure time system by 1 hour, and compare with the H-alpha.
Fine, thank you.
Yeah, on the other hand, I don't know whether some of the only stars that we are observing might be of interest to you.
Yeah.
So as to add to our project, let's say, your observation strategy for those.
From the top of my mind, I know that we are also planning to search for runaway stars that produce many of them some kind of
those shows. Yeah, those are very interesting.
That would be I don't really know on the top of my mind if this is detectable by this kind of filter. I think so. Yeah. Fine.
So I think that at some moment we may share the target list to see whether there is some possibility of collaboration among us.
Perfect. I may ask a question. I was very interested in the production of the mini Hawks the new filters. I want to know if right now people, yeah, the people from here from the TESCA have speak about the feasibility of these filters, because I'm thinking about what I present of the equivalent width of H-alpha, trying to do it only with the filter. Maybe that approach that you were thinking about is a step forward. I don't know. I was thinking of the feasibility of what they have to do if they have to do something.
Well, we have been talking yesterday with Tony about that. Well, it's a technical challenge to produce filters as narrow as the narrow H-alpha filter that I need, which has a full width maximum of only 35,000. And and to have this central wavelength and full width and maximum consistently over the whole field of view is technically challenging. We have been working on that. We have produced pilot filters for a different instrument with a company which is called OAJ, a Japanese company, and they have done a very good job. We set some very tight constraints on the tolerances of the central wavelength and full width maximum, and they managed to produce these filters within tolerances, but only for filters which have a side of 50 millimeters, which is half of the side of the filters that will be required for P80, for the camera. So well, this is promising, but we need to to basically do a proper Cmax simulation, and also, as Tony was mentioning to me yesterday, one thing is basically the opening angle of the beaming of the light, and the other problem is how consistent can be these parameters over the entire surface of the filter. And this is something that is tough for the companies to produce. But well, we have some ideas about how to do that, and we need to explore this a little bit more.
Anything else, or anything else from the virtual audience?
I think nobody's raising the hand.
Could I ask again about, sorry, the limitation on the right accession and the limitation between different projects with the similar cover, is that something that is very important for the code, or what I mean? I know that that really bright is something that is good for activity. I want to know if this is just a good hope, but not necessarily a limitation.
So that appeared in the calls for letters of intent, right? So I mean, we are considering that, and this is not going to be a strict requirement. So what the idea we tried, or we tried to transmit, is that we have to look for projects that are covering all the ranges of declination, right? So we can observe over the whole year. We cannot execute projects that are sharing exactly the same field of the year where they are observable. But I mean, I understand this is an unfortunate way to transmit that in the letter of intent, because it's creating some confusion. Of course, in the final call for proposals that still needs to be fully defined, this is not going to be, at least it is not going to be a rigid requirement. Of course, we will encourage people to cover, to design surveys that can be observed over the whole year, so that makes them more feasible. But there won't be a tight requirement. At the end, if there is an oversubscription for a part of the year, it's going to be the time and location committee, or should be the time and location committee, that decides which project has higher priority and what project has lower priority. So I wouldn't pay attention to that point. I know that is creating some confusion, but it won't be that way in the final call for proposals.
Anything else?
Macho?
No.
Ah.
So then I guess we can stop here. Just wanted to thank you all again for coming to the session. So just wanted to insist that thank you all for coming to Teruel to have this meeting in person. Thank you to all of you that are attending the meeting from abroad in the virtual version of the meeting. Again, I think has been, in my personal opinion, a very interesting, very productive, and very encouraging meeting. And just thank you, and hope we keep in touch, working on the different proposals. Just again, use CEFCA as a support infrastructure to figure out the details of your proposals, to figure out the best way to implement your scientific goals and ideas, and that's it. Thank you.